So let's just write down this gx in the general form and like it looks more precise. Although I will remark this is not really necessary, but if we express our gx in the form of one variable xn plus 1, and if there exists some gx in the same ring, Q this f, then suppose it is a form also is one variable, then this g times f equals 0 implies, compare the coefficient of xn plus 1 power, very similar as before, you got all those. And then again, very similar as exercise 2, you see that gm squared kills fn minus 1, gm cube will kill fn minus 2, etc. gm to the power and minus, it depends on what is your degree, some big power of gm. Let me just say it roughly. Say some r will kill all the fi. Okay, and so you find a polynomial that kills all the coefficients of fix. And so now by the induction you will say that this is a constant. But actually we could see it more quickly, which is, I'm feeling I made things so complicated and necessary. If there is a g such that this equals 0, if you write this in the form of one variable, and then just actually, yeah, this is what we talked about, but we are repeating what we have proved in exercise 2. One variable, this is like in b of x, polynomial which is zero divisor, imply that there exists some a or b in b such that b times this f equals 0, right? Then by induction, because this b is at this moment here, a variable, by induction there exists further b which is in just a such that bf equals 0, and so on. Okay, now it's left to deal with this last one. F is primitive, so again we have our f, all the coefficients, and I, and I, right? So I1 is defined to be all those. Similarly, I2 is for G, let's call it B and I. Sorry, this is a summation, obviously. And then correspondingly we have this f times g, whose coefficients, okay, let's call it d and I. Obviously, again, the first observation would be there is one direction very quickly, follows from the fact I3 is contained intersection I1 and I2, and so I3 equals 1 would imply I1 and I2 equals identity ideal. Conversely, we want to prove if I1 equals I2 equals 1 identity ideal, then I3 is 1. Again, this follows from the fact Fg is mapped to 0 if we quotient the coefficient ring by a maximal ideal that contains I3. Which means suppose not, which means I3 is not identity, then there exists some M containing I3, right? And then we consider this map, but the same map would have F and G both non-zero, which is a contradiction because this is integral domain. It is the integral, not even field. And so this is integral domain.